Respected judges, Assalamu alaikum. Today, we represent Team TMV Tech Titans competing at high school level for Teknofest 2026 Technologies for Humanity competition. We are proud to present our solution for transportation systems, the Guardian Wheel. My name is Mohammad Ishan and standing alongside me is my teammate Muhammad Moid Farouk. We will be your host for today. So let's start by examining the core scope of Guardian Wheel. Our main idea is an integrated vehicle safety platform that uses infrared driver monitoring alongside a 360-degree LiDAR to prevent drowsy driving trends. The solution approach evaluates eye closure and head drops locally to a Raspberry Pi. It fuses this internal data with a 50-meter external LiDAR scan to scale warning thresholds dynamically. This expected impact is monumental, delivering predictive warning 10 to 15 minutes prior to critical impairment, actively preventing global fatigue-related road fatalities before they even happen.
Our primary purpose is eliminating the reactionary gap in driver safety. Standard lane departure tools only trigger after a car physically drifts across a lane. Guardian Wheel identifies subtle psychological precursors to drowsiness, providing a proactive safety net before physical control is lost. Furthermore, we are democratizing advanced safety. Elite driver assistance is traditionally restricted to luxury vehicles. By using commercially available hardware costing approximately around $250, advanced protections become completely accessible to everyday drivers and small commercial fleets.
This brings us to the first part of the problem definition, the severe limitations of current safety technologies. First, smartphone based apps are inherently flawed. They suffer from erratic performances due to poor lighting and inconsistent camera angles, leading to excessive false negatives and distracting false positives. Secondly, conventional lane departure warning systems are strictly reactive. They trigger a panic style haptic alarm only after the vehicle is already drifted, acting as a final emergency signal rather than a preventive safeguard. Finally, standalone driver monitoring systems monitor the driver in a silo. They fail to perform essential sensor fusion, meaning they cannot correlate physiological fatigue with external environmental variables.
Continuing our problem definition, we must look at the scale and nature of drowsy driving. Drowsy driving is a silent epidemic, contributing to a significant percentage of global road fatalities. Fatigue is not an abrupt on and off state, but an progressive cognitive impairment. Drivers often fall victim to a slow insidious decay in their situational awareness and reaction times. This gradual decline renders them completely unstable to perceive their own deteriorating performance. This causes them to persist in driving even when they are significantly cognitively compromised, leading directly to catastrophic high speed collisions.
Our proposed solution integrates three critical systems to prevent these accidents. Firstly, infrared driving monitoring. A local neural network tracks the micronaut, a specific 5-degree downwards head tilt using IR data. This accurately predicts microsleeps 15 minutes before cognitive lapse. Secondly, 360-degree LiDAR sensing. A solid-state LiDAR constantly maps the external environment, tracking object density and narrow lanes up to 50 meters away. Thirdly, we introduce the risk adaptive intelligence node. The system actively fuses internal physiological risk with external macro-environmental data. If external traffic density is high, the system automatically lowers the internal fatigue alarm threshold by 30% to guarantee absolute safety.
The second part of our solution focuses on how we interact with the driver through a hierarchical intervention framework. Instead of just screaming at the driver, level 1 initiates subtle steering wheel vibration and visual alerts. Level 2 escalates to a high priority audible alarms and continuous haptic feedback. Level 3 triggers maximum alerts on optional Bluetooth emergency notifications sent to a centralized fleet hub. All of this operates on an edge first architecture. Decisions are executed locally on a physical Raspberry Pi 4. This guarantees zero latency, ensures offline reliability on dead rural highways with no cellular access, and protects drivers' privacy because video feeds never leave the cabin.
Moving to our prototype development, we executed a rigorous three-phase engineering pipeline. In phase one, machine learning and micronodes. trained a lightweight neural network to achieve a high confidence interval. It specifically tracks the 5-degree downwards head tilt using infrared data, isolating general fatigue from natural movement. In phase 2, we built the risk correlation metrics. We integrated the LiDAR data evaluating our decision making speed relative to external object density to create dynamic threshold scaling. Finally, in phase 3, edge assembly, we built the physical Raspberry Pi stack and haptic interface, proving our 15-minute predictive window and validating a full fault tolerant reliability without any cloud servers.
Looking at the specific hardware architecture of our prototype, the physical stack is built completely on commercially available open source hardware to maximize modularity and keep costs low. The perception layer features a custom infrared camera module positioned directly on the steering column for optimal facial landmarking. This is combined with dash mounted solid state LiDAR for 360 external spatial mapping for the actuation interface. We embedded custom haptic motors directly into the steering wheel. These motors provide the physical level 1 and level 2 tier interventions smoothly and safely before the system needs to trigger the aggressive audible cabin alarms.
This slide highlights our commercialization potential. Guardian Wheel achieves modular economics and an estimated cost of just around $250. Built entirely on open source hardware, it breaks the monopoly of proprietary automotive safety systems. We also provide advanced fleet analytics, optional cloud synchronization of anonymized event logs, allow logistic companies to map high fatigue routes and optimize driver schedule safely. Furthermore, the system includes a fault-tolerant watchdog. If severe weathers like heavy snow blinds the extended LiDAR, the embedded logic isolates the fault and safety downgrades to purely internal IR monitoring, ensuring that the driver is never left unprotected.
Our deployment targets four distinct demographic sectors where advanced safety is urgently needed. First, commercial fleets, logistics companies managing long haul overnight shipping routes where driver fatigue is incredibly high. Second, private owners, everyday commuters driving older vehicles without expensive factory safety packages. Third, transit authority bus and public transport operators and working repetitive, exhausting shifts. Finally, Tier 1 suppliers, automotive manufacturers seeking a low cost, highly effective sensor fusion architecture to integrate directly into future vehicle dashboards.
The expected impact of Guardian Wheel is transformative for road safety. Firstly, we are reclaiming the buffer. The system gives the driver a massive 15-minute buffer to pull over the safety, completely eradicating the deadly 2-second panic reaction when a car drifts out of its lane. Secondly, we enable data-driven logistics. Fleet managers can transition from guessing fatigue based on generic hours logged to utilizing actual physiological safety data. Ultimately, this leads to global accident reduction by directly mitigating high-speed multi-vehicle collisions caused by unresponsive drivers on in heavy commercial trucks, for instance.
Our project schedule followed a strict execution timeline. From mid June to July, we focused on training the lightweight neural network on IR data to optimize micronaut detection. Throughout July to early August, we are trying to integrate the LiDAR data and build the risk correlation matrix. Finally, from mid July to late August, we will assemble the physical Raspberry Pi stack and conduct field testing to verify a 15-minute predictive window.
Evaluating the platform objectively through a SWOT analysis, our strengths include dynamic threshold adjustments using sensor fusion, zero cloud delays due to local processing, and a highly affordable $250 plug-and-play retro profit. Weaknesses address strict mounting alignment requirements and the fact that thick polarized sunglasses or extreme slouching can temporarily force the IR cameras to lose its lock. Opportunities lie in syncing anonymized logs for fleets and partnering with commercialized auto insurers for lower premium rates. And threats involve severe mud or snow obscuring the LiDAR and future safety regulators mandating built-in cameras, which may narrow the aftermarket.
Predicting the danger so you don't have to react to the crash. This is team TMV Tech Titan signing off. Allah Hafiz.
And thank you.